Good morning to all. Welcome to my channel Firjan. Today we discuss electric charges and electric fields. In this lesson, second video, 12th standard. See here, Coulomb's law. Coulomb's law. See, Coulomb's law na, it explains about interaction between charges. Interaction between charges. See here, in this one, we can take two charges, Q1 and Q2, point charges. See, Q1, it is the Q1, it is Q2, it is the first charge, it is the second charge, which are separated by a distance r. These are separated by a distance r. See, force on first charge due to q1 q2 this direction, it will be act in this direction. Why not? This is positive q1 is positive q2. See, force on 1, force on first charge due to second one, this is the direction of force. See, force on 2, force on 2 due to first one, this is the force on second one due to first charge F21. So F12 is due to Q2 on Q1, F21 is force on 2 due to Q1. This is F21. See, these two are F12 equal to minus of F21. Why we are writing minus now here? Both are in opposite direction. See, but their magnitude F12 equal to F21, that equal to we can write F. So both are magnitude is same but opposite in direction. See, Coulomb's law na, interaction between charges. Q1, Q2 are point charges. It is one point charge, Q2 is another point charge. First one, second one. Force on 1 due to second one, it is this direction. Force on 2 due to first one, that is this direction. Both are in opposite direction. So, but force is same. See, F12 equal to minus F21. This minus indicates both are acting in opposite direction. It will be right direction, it will be left direction. F12 equal to modulus of F21, that equal to F, means their magnitude is same but their product is different. These forces F always acts along line joining center of two charges, center of two charges, means force acts along line joining two charges, center of two charges. It always acting along line joining the center of two charges. See, what is the force now here? Force is exist between the charges is always directly proportional to product of their charges. Force exist between the charges is directly proportional to product of their charges q1 and q2. It we can take one first equation. See, force exist between the charges is inversely proportional to square of the distance between them, that we can write F proportional to 1 by q square. This we can take equation 2. See, force exist between these charges is product of their charges q1 q2 and inversely proportional to square of the distance between them. See, from this 1 and 2 we can write F proportional to q1 q2 by r square. See, if you remove proportionality, we can add one constant, that is k q1 q2 by r square. This is the force exist between two charges. Force exist between two charges. What is the here? See, F equal to k q1 q2 by r square. Here k means proportionality constant. Proportionality constant. This we can write k equal to 1 by 4 pi epsilon. Here epsilon means permittivity of medium. permittivity of medium. This k value is depends on medium. Medium change na, this k value change. This k value is for free space 1 by 4 pi epsilon naught. This value is 9 into 10 power 9 Newton meter square per coulomb square. This is the for k value in free space. What na? 1 by 4 pi epsilon naught. That value is 9 into 10 power 9 Newton meter square coulomb square. See, k value for we can write for medium 4 pi epsilon m we can write. It is the medium. Other than free space or vacuum, we can write k equal to 1 by 4 pi epsilon m. See, once again, Coulomb's law na interaction between charges. See, q1, q2 are point charges. q1, it is the first charge, it is the second charge. Both are positive charges here. See, force on first one due to second one, that we can write F12. This is the direction of F12. See, force on 2 due to q1, that is this is the direction of F21. So F12, F1, F21, both are in opposite direction. How to represent now? F12 equal to minus of F21. See, but the magnitude of force exist between the two charges is same. F12 that equal to F21, that is F we can write. Means magnitude modulus of F12 equal to modulus of F21, that equal to F. The force exist between the charges is always acts along line joining center of two charges. This center, in between them it will act always along line joining the center of two charges. What is the force now? Force is directly proportional to product of their charges. Force is inversely proportional to square of the distance between them. Here it is electrostatic force, though we can write it Fe. So that from this 1 and 2 we can write F proportional to Q1 Q2 by R square. So F equal to proportionality remove, we can write K Q1 Q2 by R square. Here K is called proportionality constant. So means it is depends on medium. So depends on medium means medium change na, this k value change. For example, see k equal to 1 by 4 pi epsilon naught. This is for free space, free space or vacuum. That value is 9 into 10 power 9 Newton meter square per coulomb square. See, k equal to 1 by 4 pi epsilon. Epsilon means permittivity of medium. See, for example, medium na, k equal to we can write 1 by 4 pi epsilon m. Epsilon m. Epsilon means permittivity. See here, in this case, we discuss. See here, what f equal to q1 q2 by r square na, this is the scalar form. We can write now vector form. For example, see vector form. How to write vector form na? See, this is the first charge q1, it is the second charge q2. See, force exist on q1 f21, sorry f12. How to know this one? See, this is the center of line joining the center of charges. See, force on 1 due to 2 means here force will be, this is the direction. We can write here this radius is r2, this radius is r1. Difference na r1 minus r2. So means here radius we can write it r1 minus r2 in vector form. This is the r1 minus r2, r1 minus r2. See, force on 2 second charge is we can write F21 due to first one, that we can write it is. So this will be acting on 2, so that's why this is the direction of force. So we can write r2 minus r1. This radius is r2, this radius is r1, so r2 minus r1. So this one, see, but there see magnitude r2 minus r1 or r1 minus r2, we can write it as modulus of r, modulus of r. Now we can write what is the force exist between the charges now? K q1 q2 by r square. This one we can write, we can add multiply with the unit vector, that is, for example, here we can write f12 now, we can write f12, which is the direction, this direction, r1 minus r2. See, r1 minus r2 cap we can write multiply now, it is the vector form. For example, see, a cap equal to, how to write now? A vector by magnitude of a vector, modulus of a. So like this here, f12 force on 1 due to 2 is f12, that we can write in vector form. You can write arrow mark. So F12 arrow equal to K Q1 Q2 by R square. Here modulus of R we can write R square. So means what is the vector direction of this one? This is the direction. So R1 minus R2. We can write R1 minus R2 cap. Cap remove na. We can write F12 K Q1 Q2 by modulus of R square. Here we can write R1 minus R2 vector by modulus of R1 minus R2. R1 minus R2. See, A cap means A vector by magnitude of A. Here R1 minus R2 cap means R1 minus R2 vector by modulus of R1 minus R2. See, here modulus of R is there. We can write modulus of R is nothing but modulus of R1 minus R2 or R2 minus R1. We can write any one. So that one now finally what we can write now? F12 vector form. Force exists between the two charges will be represented in terms of vectors now. F12 equal to K Q1 Q2 by R square. R means here we can write R1 minus R2 whole square into R1 minus R2 vector by R1 minus R2 vector by modulus of R1 minus R2. See what we can write now finally. F12 force exists between the two charges is K Q1 Q2 by R1 minus R2. See here 2, here 1. So means 3 R1 minus R2 vector form. This is the vector form of force exists between two charges Q1 and Q2. See once force exists between the two charges is K F equal to K Q1 Q2 by R square. How to write in vector form now? See, for example, force on 1 due to 2. This is the direction. This is the radius initial position to final. So R1 minus R2. R1 minus R2 distance between the these charges. For example, force on 2 due to 1, that we can write this is first, this is second. So second minus R2 minus R1, that is the distance between the charges, that in vector form. See R2 minus R1, R1 minus R2, this we can write modulus of R, means both are same distance but represented for vector form. Now like this we can represent. See, force on 1 due to 2, that we can write K Q1 Q2 by modulus of R whole square. For vector form we can write multiplied with cap. So means R1 minus R2 cap. So R1 minus R2 now means for example A cap. How to write? A vector by modulus of A. So that we can write R1 minus R2 cap. Distance between we can write na vector form na. So that's why R1 minus R2 cap we can write R1 minus R2 vector by magnitude of R1 minus R2, modulus of R1 minus R2. See, R now we can write it as R1 minus R2 whole square. R square is then R1 minus R2 whole square. Here R1 minus R2 vector by R1 modulus of R1 minus R2. See here 2 into 1. So 2 plus 1 3. 2 plus 3, 2 plus 1 3. So means R1 minus R2 whole cube. Means vector form is vector form of force exists between the charges is F12 equal to K Q1 Q2 by R1 minus R2 modulus of R1 minus R2 whole cube R1 minus R2 vector R1 minus R2 vector. For example, see F21 force exists between the two charges in force on second charge due to first one, that we can write in vector form K Q1 Q2 by R2 minus R1 whole cube R2 minus R1 vector form. This is the vector form of force, electrostatic force exists between the two point charges Q1 and Q2. This is the clear information about Coulomb's law as derivation. So this is scalar form, that is vector form. In this one we have one more. See, in gravitation lesson we can learn about gravitational force, that is Fg equal to G m1 m2 by R square we can write. See this one. So electrostatic force, force exists between the two charges, force exists between the two masses. So we can relate these two. So Fe equal to K m1 sorry q1 q2 by R square. See, this is electrostatic force, this is gravitational force. See here, these two forces we can write what are the similarities, what are the differences. So we can discuss first. See, gravitational force now, force exists between two masses, point masses, that also point masses. See here, for example, see, force exists between two point masses, see m1, m2, that we can write it as F G, we can write G m1 m2 by r square. Force exists between two charges, point charges is q1 q2, that we can write it as, see, Fe, electrostatic force, equal to k q1 q2 by r square. See what are the similarities now here. See, first we can write here G value, G equal to 6.67 into 10 power minus 11 Newton meter square per kg power 2. Here K na, K equal to 9 into 10 power 9 Newton meter square coulomb square. This is the K value. It means it is gravitational constant, it is proportionality constant when between the two charges. This K value is, first we can write what are the similarities of these two forces in these two forces. See, gravitational force and electrostatic force both are inverse square law. Inverse square law means, for example, see, force and distance, we can draw the graph now here. See, force on y axis, distance on x axis, we can take, it will be get the graph like this. So means here F proportional to 1 by r square. See here, gravitational force exists between the two point masses is inversely proportional to square of the distance between them. Electrostatic force exists between the two point charges is inversely proportional to square of the distance between them. That's why we can say, so Fg means gravitational force and electrostatic force are inverse square law. Inverse square law means distance increases, a force exists between the two charges is decreases. Distance decreases, force exists between the two charges is increases. Here also same. When the distance between the two masses is decreases, force exists. Distance between the charges is increases, force decreases. So that means both are depends on distance, square of the distances. That's why we can say gravitational force and electrostatic force both are inverse square law. For example, see, radius equal to twice means force exists between the charges is 1 by 4 of initial charge. For example, radius is half now, 1 by 2 r now, force exists between the charges is 4 times initial charge. So means here, see, 4 distance increases, what happened now, force is quarter, distance decreases means force is increases. So we can say gravitational force and electrostatic force both are inverse square law, it follows inverse square law. So that's why we can say what are the similarities now. First similarities, this is the first similarity, means gravitational force and electrostatic force both follows inverse square law. Second one, see, force act along, force, electrostatic force and gravitational force always act along line joining center of charges. Center of charges. See here, these are the two similarities between the gravitational force and electrostatic force. See, gravitational force na g m1 m2 by r square, electrostatic force na k q1 q2 by r square. Both are inverse square law. Why? Because it will be depends on distance. Distance increase, force decreases. Distance here also same. Distance increase, force decreases. Here distance decrease, force increases. Distance decrease, force increases. See here, distance 2r, force is F by 4. Distance is 1 by 2r, force is 4F, increases. So that's why these are inverse square law. See, electrostatic force and gravitational force always act along line joining center of charges. See, This between them, in between the two masses, force always along the line joining charges. Here also same, force always exists along the line joining center of two charges. That's why these two are the similar properties of gravitational force and electrostatic force. See, what are the dissimilar properties now? See here, once, for example, see, first dissimilarity. First one means differences. Difference between electrostatic force and gravitational force. First difference now, see, gravitational force is independent of medium. Independent of medium, not depends upon medium. See, electrostatic force is depends on medium. Depends on medium. So will be why now k value, see, k value for a vacuum 9 into 10 power 9 Newton meter square per coulomb square. For k value means proportionality constant. This value is k value is for air medium or vacuum. For example, water medium now, it is for vacuum. Water medium now, this is 8 point. See, water medium different value. See, this value is means depends on medium. So that's 8.85 into 10 power minus 12 value. So that's why k value is different for different medium. See, Fg value means here gravitational constant na g value equal to 6.67 into 10 power minus 11 Newton meter square per coulomb square. This value. See, this value is always constant. That's why we can say gravitational force is independent of medium. Electrostatic force is depends on medium. This k value is 9 into 10 power 9 Newton meter square coulomb square. So like this it will changes. So that's why it will be depends upon medium. Second difference now, see, gravitational force is weak force. Weak force means small force. See, electrostatic force is strong force, means bigger force, strong force. See here, gravitational force is less than electrostatic force. See, for example, electrostatic force is 10 power 42 to 44 times greater than gravitational force. That's why we can say gravitational force is weak force, means small force, it is strong force. These are the differences between gravitational force and electrostatic force. First one is difference. Gravitational force is independent of medium. Electrostatic force is depends on medium. Gravitational force is weak force or small force. Electrostatic force is strong force or big force. So gravitational force is less than electrostatic force. That means electrostatic force is 10 power 42 or 44 times greater than gravitational force. Greater than gravitational force. These are the similarities and the differences between the gravitational force and the electrostatic force. Now we discuss some problems. See, for example, about Coulomb's law we discuss. See, find the ratio of electrostatic force and gravitational force for two electrons placed at some distance, placed at some apart distance apart in air medium. See, for that, for example, see how to solve this one. See, first we can write electrostatic force. What is the electrostatic force? K q1 q2 by r square. See here, k q1 by q1 q2 by r square. Two electrons na. See, k value 9 into 10 power 9 value Newton meter square per coulomb square. Q value charge na electron. So means 1.6 into 10 power minus 19 coulombs whole square. 2 charge na q into q square na. So that's 1.6 10 power minus 19 whole square. See, r square. Gravitational force g m1 m2 by r square. G value is 6.67 into 10 power minus 11 Newton meter square per kg square. Here mass of the electron 9.1 into 10 power minus 31 kg. Here we can write whole square. Why? Because 2 is the m1 m2 na. So by r square. See, these two divided na. See, this one cancel. See here 10 power minus 11, here 10 power minus 31 whole square, means here see 9 into 10 power 9 into 1.6 into 1.6 into 10 power 19 whole square na. 10 power minus 38 divided by this one 6.67 into 10 power minus 11 into 9.1 into 9.1 into 10 power minus 62 we can get. See, 62 now here cancel, means 62 minus 38 is here 4 5 3 24 plus minus 24. Yes na. See here 11 is there, minus 11 minus 11 means 5 3 35 mm, 38 62 62 1 minute. See here 62 11, what we can write 73. Here 9 we can subtract na. So means 38 minus 9 means 29. So we can subtract here 29, what we can write 4 6 to 4. So means minus 44. So means we can change this to numerator na. Here we can write 9 into 1.6 into 1.6 by 6.67 into 9.1 into 9.1. So into 10 power 44, approximately we can get 10 power 42. So means gravitational force, electrostatic force is 10 power 42 times greater than that we can write. Electrostatic force is 10 power 42 to 44 times greater than gravitational force. Gravitational force. This is the ratio of electrostatic force and gravitational force. For example, see next problem. See here, you can write the charge q is divided into two parts. When these two parts are separated by a distance r, some distance, separated by distance r, the force, electrostatic force exists between charges is maximum, is maximum, then find charge on each part, charge on each part, that we want to do. See first once again problem, the charge q is divided into two parts. Yes na. When these two parts are separated by a distance r or some distance r, the electrostatic force between the charges is exists between the charges is maximum, then find charge on each part. For example, see, first charge we can take it as first part, we can take it as x, second part we can take it as q minus x. Why na? Q is divided into two parts, one is x, another one is q minus x. So that right, this is first charge, first part, second part, these are separated by distance r. See what this now force, what is the force exist between them now? F equal to k x into q minus x by r square. Yes, now this is the force exist between the first part and second part. First part is x, second part is q minus x. F equal to k x q minus x by r square. What they said now? What they said now? See, electrostatic force exists between the charges is maximum. So means d here electrostatic force is maximum. Maximum case now we can take df by dx, df by dx equal to 0 we can take condition. See, maximum force now df by dx equal to 0 we can take. D by dx of f means k x into q minus x, yes na, by r square. This is the force between the two charges, its value is 0. See again once problem, the charge q is divided into two parts. When these two parts are separated by a distance r, the force, electrostatic force exist between the charges is maximum. Then find charge on each part. See that q is divided into two parts, one is x and other one is q minus x. Here x, here q minus x. Between the distance is r. What is the force exist between them? K q1 q2 q minus x by r square. See, this electrostatic force is maximum, they give condition. The electrostatic force exists between the charges is maximum, then find charge on each part. So that's why we can take df by dx equal to 0. D by dx of f means kx into q minus x by r square. So this this differentiate now we get the maximum. We get the charge on each part. See, first here we can write, so d by dx of kx into q, kx cube minus kx into x, kx square by r square, yes na, that equal to 0. Differentiation with respect to x na, so x part, first part k q, x differentiation means 1 dx by dx na, 1 will come, so kq minus kx square na, x square differentiation 2x, so means 2kx by r square equal to 0. This r square is changes to this side, means kq minus 2kx equal to 0. See, kq equal to we can write 2kx, kk cancel, so means 2x equal to q, x equal to q by 2. What is the each part now? Q by 2. Charge on each part is q by 2. See, the charge q is divided into two parts which are separated by distance, which are placed at r distance. The force exists between them is this one. So that force is maximum, they said. So maximum case we can take df by dx equal to 0. D by dx of f means that is the force we can write here. It's differentiate. We get kx minus kq minus 2kx by r square equal to 0. R square change this na, 0 will get kq minus 2kx equal to 0, kq equal to 2kx, kk cancel, q equal to 2x, 2x equal to q, x equal to q by 2. What is the each part na? Q by 2. This is the solution. Okay, na? See next, we discuss about superposition of, principle of superposition of charges. See, principle of superposition. What is the principle of superposition now? See, principle of superposition of charges. First na, in system of charges is there. In system of charges, in system of charges, the total force, the total force act on any one charge, act on any one charge is always vector sum of forces due to remaining all charges on this charge. This is called as principle of superposition. See here, in system of charges, the total force act on any charge is always vector sum of forces due to all remaining charges on this charge. This is called as principle of superposition. For example, see here system of charges is there Q1, Q2, Q3 is there. In between them, force on Q3. What we can write now? See, in between these two, force on Q3 due to Q1, that we can write FQ3 means F31 we can write now, plus force on 3 due to 2, so means F32. This is called principle of superposition. See, in a system of charges, the total force act on any one charge is always vector sum of forces due to remaining all charges on this charge. So that is, in this charge, due to these remaining charges, some force is acting, their vector sum is, that is, if force on Q3 is force on 3 due to Q1, force on 3 due to Q2. For example, see one more. See here, number of charges is there Q1, Q2, Q3, so on Qn charges is there. Force on n charge we can write, so means sum of vector sum of all forces due to remaining charges, means force on n due to 1 plus force on n due to second charge, due to this charge some force on this one, see force on n due to third charge, like that, plus force on n due to nth minus 1 charge. So this is the principle of superposition. Principle of superposition means in system of charges, the total force act on any one charge is always vector sum of forces due to remaining all charges on this charge. So that's the principle of superposition. See, on this we can do some problems, so we know it automatically. Yes, sir. See, for example, we can take uh, three charges which are arranged in vertices of triangle. For example, see, find net force on charge at vertex C. For example, see, we can take triangle now here. See, this is the triangle. Yes. See, equilateral triangle. Here one charge is there plus Q. Here one more charge is there plus Q. Here one more charge is there plus Q. See, we can write now here. What we can find now here? Find net force. Find net force on charge at vertex C. See, this is the A vertex, B, C. On this C, what is the net force acting on this C? That we find out. According to principle of superposition, what we can write? F net equal to force on C. Vertex C is force on C due to A means plus force on C due to B, FB. Yes, na? This one. See, first we can find out in between these two forces, what is the force exist between the A and the C, means plus Q and plus Q. We can write FA equal to force na K Q square. What is the distance now here? R distance is there in between the vertices. Yes, na? That case K Q square by R square. K Q square by R square. FA equal to. We can find out what is the force on this force. How to exist now? Acting on this direction. Why? Because positive charges is there away from the charge. It is FA. Yes, na? Due to this charge, what is the force acting now here? FB. We can write FB. So FB equal to K Q square by R square. See, Q Q K Q square by distance is R square. See, FA equal to FB, both are same magnitude is there. We can write it as FA equal to FB equal to F, we can take na, this magnitude is same na, so that's why we can take F. See, one will be this direction, one will be this direction. Here, electrostatic force is vector quantity. So we can use vector law of addition. One will be this direction, another will be direction. Here angle is there. What is the angle now? 60 degrees. Why now? See, this is the equilateral triangle. Here, what is the angle between these two forces now? 60. So resultant will be this direction is there. The resultant of FA and FB is this one. So we can use vector law of addition. So the for that F net equal to FA square plus FB square plus 2FA FB cos theta we can write root of. So this is the when two vectors adding by using vector law of addition. So that is F net equal to, according to parallelogram law of vector, see F net equal to root of FA square plus FB square plus 2FA FB cos theta. This is the formula for addition of two vectors. So F net equal to what we can write now, FA means F only, F square plus F square plus 2FF na 2F square cos 60 root of, see F net equal to means here 2F square plus 2F square into cos 60 1 by 2, this cancel, root is there, see F net equal to 3F square, so means here root to 3F, F means this two na, so K cube square by R square, so means what is the net force on charge vertex C na, root to 3 K Q square by R square. This is the net force acting on charge what at vertex C, at vertex C. What is the force na? F net equal to root 3 K Q square by R square. See again here 3 charges plus Q plus Q plus Q are arranged in equilateral triangle. So what is the force acting on charge C, vertex C, that we can write it. So due to this charge, this is the force acting Fa. Due to this charge, this is the force acting this way. These two are forces acting in different direction. See that case, we can use vector law of addition. Why? Because so electrostatic force is vector quantity. That's why we can use. See what is the force now? Fa Kq by R square. Fb is Kq by R square. Both are in same magnitude. We can take Fa equal to Fb equal to F. We can take here F net na two vectors na, sum of two vectors na, FA square, FB square, 2FA, FB cos theta we can write. FA means F only, F square, 2F square cos 60. Cos 60 na 1 by 2, 2 cancel, 2F square plus F square, 3F square. So means F net equal root of 3F square means root 3F. F means this is the K Q square by R square. So means what is the net force acting on charge at vertex C na, root 3 K Q square by R square, root 3 K Q square by R square. So this is the problem. See next problem we can see na. See once same we can take triangle, equilateral triangle, but so we can change the charges. See for example, find F net on charge at vertex A we can write it. See for example, triangle na, this one. This is the triangle ABC, A, B, C. Here minus Q, yeah, here plus Q, here plus Q. In between these two is, this is the force. In between these two is, this is the force. See here angle is 60 degrees. I write here F A force on A due to C, force on A due to B. That is F C I write this, due to this what is the force acting in this one? K Q means distance is here, R distance only. This is R, this also R distance. That case K Q square by R square. Why now? K Q1 Q2 by R square. Q1 is Q, Q2 also Q, Q by r square, means k cube by r square. Force between these two now here, force on A due to B is Fb, we can write k q square by r square. Both are in same magnitude, so we can write Fb equal to Fc equal to F. That means here, see, we can take now this one magnitude is same, so that's why we can take both now two vectors. See, this is one direction, this one, so resultant will be this direction. That resultant force we find out now. So F net equal to what we can write now, root of first force F square plus F square plus 2 F cos 60 we can write. So like before only, F net equal to F square plus F square plus 2F square cos 60 na 1 by 2 we can write. See, F net equal to 3F square 3F square, that we can write root 3F. What is the net force acting on vertex, acting on charge vertex in a root 3F, that is root 3 k q square by r square. This is the force acting on charge at vertex A. So this is the force. Yes na? See this one. Next we discuss now. Third, next problem. So when charges are arranged in quadrilateral, see for example square. See, find net force. Net force on charge at vertex C. How to arrange now this one? See, here square, here plus q, here plus q, here plus q, here plus q. See, distance is A, this distance is A, this distance also A, this distance is A. See now here, what is the na? This is A vertex, B, C, D. What is the net force on this point? We want to find out. See, due to B, what is the force acting now? Here, this is the direction of force on Q, Fp. Force on C due to B, Fb. That is force on C due to D. That is Fd here. Force on A due to A means that is Fa, we can write it. First find out now one by one. See, force on C due to, we can write first B. What is the force on B? Force on C due to B, that is Fb equal to, what is the force formula? K q1 q2 by r square. K q1 q2 means K q square by r square, means r means here A, distance between them, so means A square. This is the force. See, force on C due to D. See, that is force on D, force on C due to D, that is K q square by A square. See, force on C due to A. This side is A. Distance between the charges is A. Here distance between the charges is A. But here diagonal na, this distance is A root 2. Means root 2 times its side. So diagonal of the square is root 2 times its square. So that's why here radius is here r equal to A root 2. Here r equal to A. Here equal to r equal to A. Here also r equal to A. So but here what is the distance is A root 2. So that way we can write force on C due to A is what we can write now, K q means q square by distance is what, A root 2. A root 2 whole square means what we can write, K q square by 2A square. Yes na? See, now we can take K F equal to K q square by A square. We can take F na here. Force on C due to B is, we can write F, we can write force on C due to D we can write F force on C due to A we can write 1 by 2 F. See these three forces acting on the charge C. So that sum we find out now. For that, see this will be one direction, this one direction, this one direction. So means this force is vector quantity now. We can't add directly. So that's why these two forces resultant we can find out that resultant will be in the direction of A. So then we can add. So means F B plus FD we find out first. FD is what? FCB, FCD also F. So that resultant we can write. So FCB plus FCD, that means FB plus FD we find out. For that we can use vector law of addition, that we can write F net. So F net equal to what now? F square plus F square plus 2FF cos 60. Why now we are writing? So sum of two vectors is A square plus B square plus 2AB cos theta. A means here what? F. B means F. So means 2FF cos 60. See here F net equal to here 2F square plus 2 here cos 60, not cos 60. Here see right angle na. See why na? In square all angles are 90. So here we can write cos 90. Cos 90 is 0. So we can write 2f square. See we can write f net equal to what na here? Root 2f. See this resultant is root 2f. Now we can add. Why? Because both are in same direction na. See f net equal to total force equal to fa plus FB plus FD, that is what we can write now FA na FA what 1 by 2 F 1 by 2 F plus FB and FC means root 2 F. So F common na see 1 by 2 plus root 2, that means F net equal to root 2 plus 1 by 2 into F means kq square by a square. This is the net force acting on charge at vertex C. What is the total force acting on vertex C na? So root 2 plus 1 by 2 kq square by a square. What we are doing here first, charges plus q plus q plus q plus q arrange at vertices of the square. So what is the force on this charge we find out. For that we can use principle of superposition. First force on C due to B, that is kq square by a square. Force on C due to D, that is kq square by a square. Force on C due to A, that is kq square by a root 2. Why? Because now here distance between A and C, length of the diagonal. So length of diagonal is root times of side. That's why we can take here a root 2 whole square, kq square by 2a square. So we get this one forces. See, one will be right direction, one will be downward, one will be different direction. So this we can take sum now. For that this and this resultant we find out by using vector law of addition. So that is FCB means FB is F, FD is F. So their sum is vector sum is F net equal to F square plus F square plus 2FF cos 90. Cos 90 0 na. So 2F square plus 0. So we can write root 2F. So means this FD and FB resultant is root 2F. So FC, FA same. This now it is will be in same direction. So we can add these two directly. So means F net means FA plus FB and FD. Their sum is root 2F. This is 1 by 2F. So we can write F common now 1 by 2 plus root 2. So means we can write root 2 plus 1 by 2 kq square by a square. Next na. See now we can find another one. See, let's solve another problem. So that is first to see here, third charge is in equilibrium type questions. For example, see, where should we keep third charge? On line joining the two charges, then third charge is in equilibrium. Question I write first here, where should where should we keep third charge third charge on line joining two charges such that third charge is in equilibrium. In equilibrium. See what is the question now? Where should we keep third charge on line joining two charges such that third charge is in equilibrium? For example, see this is the first charge, this is the another charge, for example 4q. In between these two charges, here in between on line joining these charges, somewhere here we can keep q charge. Where should we keep this q charge? Then this charge is at equilibrium. Equilibrium means F net is due to this some force is acting this direction, due to this some force is acting this direction, these two forces are opposite and their sum is 0. That case, see means F net equal to 0 means net force on q is 0, then we can say q is in equilibrium, means this is the third charge, then it is in equilibrium. For that what we can do now, here see, so net force is 0 now, means for example force on first charge due to second charge, see force on q due to first charge, this is the direction, we can write F1. Force on q due to second charge, that we can write F2. See F1 I write, F1 is force on q due to this charge, means k q by distance. For example, see it is the L distance, both are separated by L distance. This distance we can take x, this distance automatically L minus x. Understood at this point? See, where should we keep third charge? On line joining two charges such that third charge is in equilibrium. For that, first charge is q, second charge is 4q, third charge is capital Q. So third charge is in between this line joining two charges, we can keep somewhere. Then F net acting on the charge is 0. So F net equal to 0. That then only q is in the equilibrium. For that, these are separated by a distance L. For example, at x distance, we can keep q. In between q and small q is x distance, automatically 4q and q is L minus x. So now we can find out force on capital Q due to first charge is this direction, force on capital Q due to 4q is this direction. So that is F1 F2. F net equal to 0 means F1 minus F2 or F2 minus F1 equal to 0. That means F1 equal to F2 only. So first we can find out what is F1. So F1 means between these. What is the charge Q? Another charge is small q. Distance is x. K q by x square. F1. F2 is discharges k q, another charge is 4q by distance between them L minus x whole square. Yes, now force exists between two charges is k q1 q2 by r square. Here is rx, q1 is capital Q, q2 is small q. Here r is L minus x whole square, one q is small q, capital Q, another one is 4q. So means F1 F2. See here, this charge is third charge is in equilibrium, means whatever the force acting on this charge is 0, net charge is 0. So that means here F net equal to 0, either F1 minus F2 equal to 0 or F2 minus F1 equal to 0. Which one is larger? That one we can write first, later second one smaller one we can write equal to 0. So means from that what we can write, F1 equal to F2. We can take this is the condition when third charge is in equilibrium. For that, see first F1. What is the F1 here? See F1 is k q small q by x square. F2 k means 4 k small q capital Q by L minus x whole square. See L minus x whole square. See k cancel, q cancel, small q cancel. What we have? 1 by x square, that equal to 4 by L minus x whole square. See This will be changes to here L minus x whole square by x square equal to 4. See, both square is there. We can write L minus by x whole square we can write. That is, this we can write square. Square square cancel. Means L minus x by x equal to 2 we can take. Plus or minus 2 we can take plus 2. So that case what we can write? L minus x equal to 2x. L equal to 2x plus x, L equal to 3x, x equal to L by 3. What is the distance now? At what distance third charge is in equilibrium now? L by 3 distance from smaller charge. See, third charge is in at L by 3 distance from smaller charge, from smaller charge. Yes na? At what distance na? L by 3 distance. At L by 3 distance, this q, what is the net force acting on capital Q na? That is 0. So then third charge is in equilibrium. Understood now this one? First q and 4q both are separated by L distance. At x distance we can keep capital Q. So automatically L minus x distance, this we find out due to this F1, due to this F2. F1 we can find out, F2 we can find out. F1 minus F2 equal to 0 or F2 minus F1 equal to 0. From that F1 equal to F2. Why? Because F net equal to 0. So that's why. So F1 equal to F2. F1 we can write, F2 we can write. Simplification, we get x value. At what distance on line joining two charges, third charge is equilibrium na L by 3 distance from the smaller charge. From the smaller charge. For this shortcut we can use what na? Shortcut C, Q and 4Q. Yes na? These two are at L distance. This case, what is the shortcut now for this? Distance from smaller charge, where third charge is in equilibrium na? For that, see, x equal to Q1. For example, this is the Q1, Q2. So means Q1 by root of Q1 by root of Q2 plus root of q1 into what is the distance between charges? L. See, x equal to root of q1 by root of q2 plus root of q1 into L. See, for example, q1 is what? Q root to q by q2 is 4q root 4q plus q1 is root to q into L. Yes na? See, x equal to root to q. Here 2 root to q plus root to q means root to q by 2 plus 1, 3 root to q into L. Q cancel. What we get? X equal to L by 3. We get na same value. See, here x equal to what? L by 3. Here also x equal to L by 3. Means what is the shortcut for this na? When two charges in same line, when third charge is placed, the third charge is in equilibrium condition na? Means where should we keep third charge on line joining two charges na? For that condition, x equal to root of q1 first charge by root of second charge plus root of first charge into distance between the two charges. Then we can use, this is the shortcut formula for finding where should we keep third charges on line joining the two charges in equilibrium na? For that we can use, this is the shortcut formula. What now that one? This is, see, root of q1 by root of q2 plus q1 into L into L. Yes na? Okay, next see, next problem, where should we keep third charge on line joining two charges before we can take plus plus positive charges or negative charges? Now we can take one positive charge, one negative charge. That case, for example, see here q, here we can take minus 9q, 9q. This case, see, distance between the charges is L distance, where we can keep third charge na? At outside the smaller charge. See here, here we can keep smaller charge, this point. See, This distance is L. Q2 smaller charge to this is X distance. This distance is force between the capital Q and 9Q is L plus X. L plus X. Then only why na force on Q is this direction due to first charge. Force on capital Q due to 9Q is this direction, that is F2. Both are in same direction. One will be plus, one will be minus. So means here this one is force on Q due to first charge is force on capital Q due to first charge is F1. We can write F1 is K capital Q small q by x square. Force on capital Q due to second charge is K capital Q minus 9Q minus 9Q by L plus X whole square. L plus X whole square. Their net force is 0. Then only third charge is in equilibrium. See, force on capital Q due to first charge. This is the first charge. This is the second charge. For example, due to this charge, force is acting on this one. That is F1. Due to this charge, force is acting on this one. F2. Both are F1 and F2 are in same direction, but it are in opposite charges. That's why net force acting on third charge is 0. So means where should we keep now? For that we can find out that one. So means here also F net equal to 0. Yes, now means F1 equal to F2. So F1 means here I write what is the force on first charge capital Q now due to first charge, that is K capital Q small q by x square. What is the force on second charge now due to second charge now, that is K 9K Q capital Q small q by x square L plus x square L plus x whole square L plus x whole square. See, this k cancel, q cancel, small q cancel. What we get? 1 by x square equal to 9 by L plus x whole square. It will changes to here now 9 L plus x whole square by x square equal to 9. Yeah, L plus x by x whole square equal to 3 square. We can write square cancel. What we get now? L plus x by x equal to 3. L plus x equal to 3x. So L equal to 3x minus x, that is L equal to 2x, x equal to L by 2. At what distance third charge is in equilibrium na? L by 2 distance outside the smaller charge. Yes na? See, we can write third charge is in equilibrium at L by d2 distance outside the smaller charge. See, third charge is equilibrium at L by 2 distance from smaller charge outside the smaller charge, so that is the, so this is one. So for example, for this shortcut is, for example, see, one is plus and one is minus na, we can use here. See, 9q na, this one. See, shortcut formula is x equal to root of q1 first charge by root of q2 minus q1. See, into L. See, x equal to root of q1 means q, root q by q2 means 9q minus q into L. See here, x equal to root q by 3 root q minus q into L. See here, what we can write now here, next step. See, x equal to root q by 3 minus 1, 2 root q. Yes na? Into L. Q cancel, means x equal to what? L by 2. At what distance third charge is in equilibrium? L by 2. We can use, this is the process, or we can use, this is the shortcut. Where should we can keep third charge is in equilibrium? When two charges are in opposite charging, opposite sign is there. Here plus q, it is minus q, that case. Plus na, both plus na, we can use another one. This is minus and plus na, this is the case. Q1 by root of q2 minus q1 into L. So what we get? L by 2. Okay na? This is the Where should we keep third charge? On line joining two charges such that third charge is in equilibrium. For plus and minus charges, opposite charges, where not third charge is placed outside to outside from the smaller charge, outside from the smaller charge. Next, so last one we can discuss this one. See, if q naught is slightly displaced along line joining 1 and 2 towards any of charge, any of charge such that q naught executes simple harmonic motion, simple harmonic motion. So find time period of such simple harmonic motion, such a simple harmonic motion. This is the problem. See once, if q naught is slightly displaced along line joining 1 and 2 towards any of charge such that q naught executes simple harmonic motion. So find time period of such simple harmonic motion. For example, see, this is the first charge, this is the second charge, yes na? In between them, here charge is there. See, this is the 2a distance, this distance is a, this distance is a also. Here charge q naught is there, it is slightly displaced, here displaced, here q naught is there. Due to this slightly displaced, it will oscillate in simple harmonic motion, it is in simple harmonic motion. That case, what is the time period of this simple harmonic motion? We can write it here q, here q, two charges is there along line joining these two charges, q naught is there, one more charge, it is slightly displaced. That case, it executes a simple harmonic motion. So that case, what is the time period of such simple harmonic motion? That we find out. See here, see, this is due to this is the force acting here. Due to this is the force acting this direction. See this one, for example, F1 we can write due to first charge, due to second charge we can write F2. See which one is greater now? Here see, smaller distance. Why not? It is a plus x distance. Yes, now from here to here. This is the position. So from here to here, a minus x distance. See what is the net force on this q naught now? See, F1 is less than F2. So we can write F net equal to F2 minus F1 we can write. F net equal to what? F2 minus F1. See, F2 minus F1, F net equal to F2 means we can write first here F1. F1 means this and this. See, K Q Q naught by a plus x whole square. F2 is K Q naught by a minus x whole square. Yes na? See here, it is the q naught. So means this is the position actually, at center is there, slightly we can displace, it executes simple harmonic motion. That case, what is the time period? We find out. For that, due to this, after displacing x small x distance, force acting on that one is F1, this direction. And after displacing x distance, what is the force due to this second charge? Is this direction, F2. F2. Both are in opposite direction. See this case, which is smaller to this one, smaller distance, that have more force. Bigger distance now, larger distance, that is have smaller force. So means F1 is less than F2. F2 is greater force. So that's why we can write F net equal to F2 minus F1. So F2 is what here? K Q Q naught by a minus x whole square minus k q naught by a plus x whole square. Yes na, see here f net equal to k q naught we common, what we can write now here 1 by a minus x whole square minus 1 by a plus x whole square. Yes na, see we can write here k f net equal to k q naught. Here LCM we can take na a minus x a plus x whole square na, see here this one LCM, this one cross multiplication 1 into a plus x whole square, a plus x whole square, this one a minus x whole square. See a plus b whole square minus a minus b whole square, we can write k q naught into 4ax. Why na? A plus b whole square minus a minus b whole square equal to 4ab. That is the formula. Yes na? We can use here k q naught 4ax by here a minus x a plus x means a plus b into a minus b na a square minus b square. So we can write a square minus x square whole power 2. Yes na? See a square minus x square. See before that x is very small to a. So means a x square means tends to 0 only na. So we can write here instead of x square we can write 0. So means k q naught 4ax by a square whole square. So what we get now here k q naught 4ax by a power 4 means 1a cancel now a cube we get means what is the f net now here k q naught 4x by a cube, we get this one. See this is the net force acting on this one, so that will be comparing with simple harmonic motion. Now what is the force now for that? So f equal to minus kx na, minus kx we can take here minus kx dash, here f net equal to k 4k q naught x by a power 3. Here we can take minus, see that equal to minus kx na, this k dash this value same means k dash equal to 4k q naught by a cube. What is the time period formula na? 2 pi into root of m by k dash we can write. So time period equal to 2 pi root of m by k dash means 4k q naught by a cube means time period equal to 2 pi root of m a cubed by 4k q naught. This is the time period of simple harmonic motion when the particle is slightly q naught is slightly displaced from its center. So this is the process. See what we can do now here q charges is there, it will be slightly displaced, it executes simple harmonic motion. One force is acting this direction, another will be acting this direction. Force first one is k q by q naught by a plus x square. Force f2 na k q naught by a minus x square. F net na f2 minus f1. Why we are writing f2 minus f1 na? F2 is greater than f1, that's why. So k q naught by a minus x whole square minus k q naught by a plus x whole square. Here k q naught common, 1 by a minus x whole